Okay, so finding the points of inflection, that's really similar to what we did on the previous problem. We even talked about finding that point of inflection, and that's where we're going to try and find that second derivative and where the sign changes from plus to minus on a sign chart. So if I have the derivative of this guy, that's going to be e to the negative x squared times the derivative on the top, which is this. So negative 2x e to the negative x squared. The second derivative then is now going to require some product rule. So it's the derivative of the first times the second plus the first times the derivative of the second. Well, e to the negative x squared. Well, let me just back up. We know exactly what that is. It's going to be the first times the second, the derivative of the second. Well, there's the derivative of e to the negative x squared. So negative 2x e to the negative x squared. All right, so clean this up just a little bit so we can sort through what's going on here. And this is negative 2 e to the negative x squared plus 4x squared e to the negative x squared, and we want to know where that equals 0. Well, looking at it this way is really tough. It's hard to say exactly, but if you'll notice, I have an e to the x squared right here and an e to the negative x squared right here, so I can factor that out. And when I do that, I end up with negative 2 plus 4x squared. And so what I do is I set that both pieces equal to 0. So that e to the x, e negative x squared equals 0. And does that ever happen? No, it doesn't. It's always bigger than 0. And then I go with the other guy, negative 2 plus 4x squared equals 0. And I just am going to solve this guy out. I'll move up here and have a little more room. So this is going to be 4x squared equals 2, so x squared equals a half, and so x equals 1 over, plus or minus 1 over the square root of 2. And so I just make my sign chart, and I use the plus or minus 1 over the square roots of 2's to work this out. So I got negative 1 over radical 2 and positive 1 over radical 2. And those are the two places that I'm going to check. And I check it in that second derivative, in the two pieces of the second derivative. Here's one piece right here. Here's one piece right here. Okay, so we saw that e to the negative x squared will always be positive no matter what. Okay, but now we just need to look at what's going on then when we plug these values into negative 2 plus 4x squared. And again, I just need to know the sign. What's the sign? Is it positive or negative? So we want to pick a number less than 1 divided by radical 2. So, you know, a real safe number in this case might be negative 3. Okay? So pick negative 3. Make sure that you're picking a number that's well into that area. So I put negative 3 in here, and I'm going to get negative 3 squared, which is 9. Okay, times 4, which is 36 minus 2, so I'm going to get a positive number. And then I'm going to pick a 0, and when I put 0 into negative 2 plus 4x squared, I end up with a negative. And then pick another number larger than 1 divided by square root of 2. And if you need to know what that is, punch it in on your calculator, get a decimally answer, and when you've done that, then find a larger value. But you could use something like even say 5. So, and again, just like the over here, way over here on the left, you're going to end up with negative 2 plus 4 times 25, and that's a positive. So what does that mean? That means that I am concave up here, I'm concave down here, I'm concave up here. Why? Because I have a minus sign, a plus sign, and a plus sign. So I've found my points of concavity. My points of concavity, my points of inflection are right here at these two points. They are my points of inflection. So when x equals negative 1 over root 2, and when x equals positive 1 over root 2, I get that point of inflection for my graph. Now, where does that occur? I don't know. What I can do, though, is I take this negative 1 over square root of 2 and plug it into my original function. And the reason I plug it into my original function is I want the point of concavity for my function for y equals negative x squared. And so to find that, I'm just going to go y equals e to the negative x. What is my x? Well, it's negative 1 over root 2 squared. Okay? Well, what is that? 1 over the square root of 2 squared is 1/2. All right, a negative 1/2. So my y value then for this guy is e to the negative 1/2, and it's going to be the same thing over here. So both of those guys will be points of inflection for this particular problem. So I'll write them right here. So I've got the point of inflection is going to be negative 1 over root 2 e to the negative 1/2 and 1 over root 2 e to the negative 1/2. Both of those will be points of inflection for this particular problem. Now, why don't you try x cubed minus 12x minus 5? It's a lot easier to work with. You don't get any like really totally horrible numbers. You may get a decimal or a fraction or something like that. You try it out, pause the video, you try it out, and I'll show you the answer when you start your video back up. All right, so first derivative, did you get it right? Whoa, wrong button, wrong button. Y prime is 3x squared minus 12. Second derivative is 6x. So we just need to know where 6x is equal to 0. And again, it's that's not too bad. It's at 0. So when I work out a little quick sign chart, I've got 0 here, and I've got 6x right here. And pick a number. Pick any number. Pick -1, pick +2, and you get negative, positive. So what's your point of inflection? Point of inflection occurs when x equals 0 because we're concave down, then concave up. So what y value is that? I don't know, but I can plug it back into my original function. So when I look at f of 0, I get 0 cubed minus 12 times 0 minus 5, which ends up being the point 0, negative 5 as my point of inflection. That's where my graph turns from concave down to concave up. Well, second derivative test. The really cool thing with this is you can find out where your local max and mins are based off of the second derivative. So you don't always need to use first derivative rules. In fact, if you want to take a second derivative, all we're looking for maximum is where your second derivative is less than 0. That's a little bit weird thinking, but it's true. And that gives you a local max. If you want your local min, try and find where your second derivative is greater than 0. That will be where your local min is. And so we can use that second derivative test. Now, sometimes that second derivative test is really difficult. Like there's a lot going on and we don't want to go that. We would rather solve it out from that first derivative spot. But sometimes finding that second derivative isn't too bad. And we can find where that maximum or minimum value occur.